Okay, folks, I think it's time for us to get going. Whoops. So let me remind you of where we are in the development of our rotational story. We started by looking at things rotating around nice frictionless axles and dropping things that weren't rotating on things that were rotating, or bringing out the stool and spinning people around and waiting for them to throw up. You may remember one of these. And what we discovered was that just as an object that is not acted upon by an external force will continue to move at constant velocity, an object that's rotating and is not acted upon by outside influences will continue to rotate at constant angular velocity omega. And we have three different ways so far of denoting angular velocity. So omega is the analog of v, but of course it means the time rate of change of angular position, theta. And we also use the dot notation to mean a derivative with respect to time. And this is more complicated than P equals mv because this moment of inertia is a more complicated beast. It involves adding up for all the different masses, the sum of the mass times whatever this r sub I thing squared is. What is r sub I? What does that stand for? Don't you dare say radius. Distance from the axis of rotation. Okay, so you go straight to the axis of rotation. That's what this r sub I means, and that's what this r means. And dm means just a little bit of mass. Add it all up for all the masses. And then we saw a little movie of a crane operator's hell, where the recipe for a good day was that the net torque remained zero and the net force was zero. And if it isn't moving and those two things are true, then you will have static equilibrium and it won't move. But statics is really great when you're building a building that you don't want, for instance, to fall over. But sometimes you want to move. And so today we get to move on and worry about, well, what happens if all the torques don't sum to zero? How does that change the angular momentum? And so let me remind you, torque was the product of the perpendicular distance from an axis to the point of application of a force, that's this r perpendicular, multiplying the force. Or you can choose instead to resolve the force into the component perpendicular to that distance from the axis, that vector. And either one gives you the same expression for the torque. And today's theme is that torque causes a change in angular momentum.